of quantum communication protocols and their application. Ma'am, the stage is all yours.
Okay, so thank you. So I shared the screen. So my screen is visible.
Yes, ma'am.
Hello. Okay.
Yes, ma'am, the screen is
Okay. So
visible.
thank. Okay. So changes are seen, right? I am changing this. Hello. Hello. Can
Yes,
you see the screen changing?
yes, ma'am, we can
Hello.
see the screen. Hello? Yes, ma'am.
Okay. Thanks. Uh, yes. Sorry. Okay. So I start. So today I will be continuing to talk about quantum communication networks. So as we have discussed in the last talk that any communication protocol requires at least two parties to be involved. So one can be a sender, another can be a receiver. And typically we call sender to be Alice and receiver to be Bob. Now, the sender's task is to send certain information to Bob, and uh, more importantly, sender and receiver are situated in two distant locations. It can be two cities, for example, in India or in different countries, and so on. Now, as I emphasized last day, that first two lectures that I have, so last day and today, I will be talking about the communication protocols that do not involve security aspects. Uh, so the yes, last day, Friday, I was talking about classical information transmission via quantum states, which we call to be quantum dense coding. And today I will be talking about quantum state transmission using quantum states. As I said, that yesterday, I mean, last day and today, I will be talking about communication protocols which are without security. And tomorrow, I will be talk about secure quantum communications, in other words, quantum cryptography. Now, what do I mean by secure communication, etc.? It will be clear when tomorrow, when I will be talking about. So, as I said, today I will be talking about quantum state transfer protocol. So, this state transfer protocol is known as quantum teleportation, which we will be discussing today in detail. And this was discovered by these six people. So, Bennett, Brassard, Tripio, Jodsa, Asha Perez, and William Wouters. So this was published in Physical Review Letters in 1993. Now, the task in teleportation is to send an arbitrary quantum state from the sender's node to a receiver nodes. Now, before I start, just a hello. Can you see my screen? Hello.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes,
Okay. Thank you. Okay. So as I said, that the task is to send an arbitrary quantum state to the receiver. So, for example, arbitrary quantum state that last day already we discussed. This is means that arbitrary qubit to Bob. So Alice wants to send an arbitrary qubit to Bob. Now, as we have discussed last day, that the basic unit in a classical computer is bit, which is one of the zeros and one. On the other hand, quantum bit is an arbitrary quantum state in a two-dimensional complex Hilbert space, which can be represented by alpha up plus beta down, where up down can also be, I mean, in a similar fashion like a classical computer unit, we can just map this up as zeros and down as one. So up down are the spin degrees of freedom of in any quantum system, and up down can be thought of as an eigenvector of sigma z. It can be any eigenvector or two orthogonal states. It can be eigenvector of sigma x, the Pauli matrix, and so on. So in general, the qubit can be represented as alpha 0 plus beta 1, where alpha beta are an arbitrary complex number, but due to normalization constraints in quantum mechanics, we have that mod alpha square plus mod beta square is equal to 1. This entire thing we have discussed last day. So in some sense that as I last day told you that it can be analogously thought of that the poles represents the two orthogonal states, so up spin or the zero and a down, that means one, and all the points in the surface of the sphere can represent this qubit. So this actually is an analogous way to describe qubit, and to understand that the only the poles are somehow the part of a classical computer. On the other hand, when we want to build any quantum protocols, whether quantum computer, quantum sensors, quantum communication, then actually we can exploit all the points which are lying in the surface of the sphere. And this actually gives you a kind of idea or the flavor that the qubit space is much bigger than the classical computer, which has only two options, 0 and 1. So as I said that this is just an arbitrary element in a two-dimensional complex Hilbert space, which is this alpha 0 plus beta 1. Last day we have also discussed about entangled state. So we said that a joint or the composite quantum system is said to be unentangled, or these states are typically useless states in any quantum protocols that typically we discuss. These states can be mathematically can be written as phi a tensor product phi b. So you can think of a preparation procedure that Alice and Bob situated in two distant locations. Alice prepares a quantum state phi a, Bob prepares a quantum state phi b. Then the joint state looks like that, which are all unentangled state. So these are this is the definition of unentangled state in when we talk about pure states. And the entangled states are those states which cannot be written as phi a tensor product phi b. And one of the prominent example is the singlet state or the triplet states, and which in quantum information science we call it Bell state. Now these states Alice and Bob cannot prepare when they are situated into distant location. And as we discussed last day, that there will be some source which can create an entangled state and can send one particle to Alice, another particle to Bob. Last day we discussed also about the photon experiment. So in case of photonic experiment, you can think that the source can be some nonlinear crystal like BBO crystal, where you push the laser and one particle will actually follow one arm, another will be following another arm. Today also we will discuss about some experiment. So this is the basic things that we have discussed last day and which we will use also today. So we will be showing, so last day I have shown that if you use this entangled state, for example, the singlet state, then you can send much more efficiently classical information, that is bits. Today we will be showing actually the efficiency. Last time I have shown that the capacity gets double, and today we will show a exponential advantage in some sense, a kind of infinite capacity enhancement by using entangled state shaped by Alice and Bob. So yes. Okay. So suppose Alice wants to send an arbitrary state, that is qubit, to Bob. So this is the task, as I said. This can be photon, polarization degrees of freedom of a photon, can be ions, internal levels, and so on. So what is the way to send? Now one can think that you just put the this input state that Alice wants to send in a box and can send it to via post office or via, say, any other medium. Okay. So you put the input state in a box, which of course can, I assume that the box is I made in such a way that it can keep the quantum state as it is. And then just like we send flowers to our friends or relatives, we just send that box to the receiver. But this kind of physical sending is not allowed. So if I assume that, then I have to design a quantum protocol by which you can send this arbitrary quantum state to Bob. So now let's discuss what about the classical device, that means the phone call that we use or the email and so on. If I want to send the informations or if I want to send an arbitrary qubit to Bob. Now you can, as I have discussed, that any qubit actually is any arbitrary point in the surface of the sphere. And in the surface of the sphere, there are an infinite number of points. And so, if we use classical bits to encode this infinite number of points, we require infinitely large string of zeros and one. That means you require infinite number of bits to send an arbitrary qubit to Bob. And so this is an infinite amount of classical communication if I want to send an arbitrary qubit to Bob. And what do I mean by arbitrary? That means this alpha, beta are unknown, and this can be any value. Now here I just want to say that even when alpha, beta are known, you still need infinite amount of classical communication, because when we actually send any information in a classical world, you actually have to somehow encode it in a orthogonal states. So to send this alpha up plus beta down, whether alpha beta are known or unknown, you actually require infinitely long bit strings. And so you, whatever smart protocol you can design in a classical device to send an arbitrary qubit, you requires infinite amount of classical communication, that means infinitely long bit string. Now let's see whether we can get some higher efficiency over the classical protocol if we use quantum mechanical systems. So again, the Alice has this input state with her, and Alice wants to send this input state to Bob, and that means an arbitrary qubit to Bob. Now here again, we assume that Alice and Bob share an entangled state, which is this singlet state, a priori. So this is what we discussed last day. This is the quantum bridge that Alice and Bob share, and this they will use to send this arbitrary qubit to Bob. So this is the scenario. Now how to do it? Now just yes. Hello, hello. Okay. Okay, so just before I tell the protocol, I just want to say that this is the scenario that Alice has this input state, this phi, the arbitrary qubit, which I write like alpha 0 plus beta 1. So this is Alice's position. And similarly, Alice and Bob shared this entangled state. This up and down can be, as I said, that it can be with zeros, 0 and 1. So this is 0, 1 minus 1, 0. And so the first one, this qubit, is in Alice's possession. So these two are in Alice's possession. And this is with the Bob's possession. Okay. So the entire system, this is a kind of three-party system you can think of, and this actually looks like that. So alpha, if I just multiply it, kind of, this is a tensor product Hilbert space, so this will be like that. And now the orange lines that I have drawn, they are in a position with Alice. On the other hand, undashed lines are undashed systems are in position with Bob. Now Alice performs measurement on the parties of input and her one part of the singlet state. And this measurement is performed, the Bell measurement that we have discussed also last day. So this is this up down plus minus down up, and up up plus minus down down. So this is the singlet and triplet state, which can also be represented as 0 0 plus minus 1 1 and 0 1 plus minus 1 0. So Alice wants to send this input state. So Alice performs a measurement on her part of the system, on her part of the singlet state, and on the input state. This is the joint measurement that Alice performs. So what do I mean by performing measurement? So as we have said that this is the entire system that's shared between Alice and Bob, which also includes this input state. Now, when we perform measurement, as we have discussed last day, we actually have to kind of taking the inner product with this, suppose this inner product with the measurement outcome. Suppose 0 0 plus 1 1 click. That means I have to take a inner product of 0 0 plus 1 1 with the entire system. And I will see that what state it has projected. So the here, as I said, that these are the first two parties, first two terms are with Alice. Now, when 0 0 and 1 1 clicks, only 0 0 and this first and last term contribute. And as you see, it will be alpha 1 minus beta 0. Similarly, you can do this algebra. And so after measurement, Alice's system, now these two systems will be in entangled state, one of the Bell state, and Bob, the correlation between Alice and Bob's are gone. Now, Alice communicates 2 bits of classical communication to Bob. Why 2 bits? Because there are 4 outcomes, and as we discussed last day in details, that 4 outcome means log of base to 4 bits, and that means 2 bits of classical communications about the measurement outcomes to Bob. So Alice is performing measurement, one of them will click, and Alice will send that information via phone call or via internet email to Bob. Now, this classical communication is extremely important that I will discuss in a minute. And depending on this measurement results that Alice has obtained, so for example, whether it is 0 0 plus 1 1, that is up up plus down down, or up down plus down up, whatever measurement outcome Alice has obtained, Bob has to perform some unitary operation. So that means if the measurement outcome is psi minus, Bob doesn't perform anything. If psi plus, then Bob performs a sigma z, phi minus sigma x, phi plus sigma y. These are the Pauli matrices, and this is the identity operator. So Bob has to perform one of the unitary operator to recover the state that Alice is sending. So after the entire protocol, one can do this algebra. This is a very simple way to, uh, I mean, you have to just do the simple algebra in quantum mechanics. Then you can find that the state that Alice wants to send, this input state, is with in positions with Bob. And so here we only have used 2 bits of classical communication to send this arbitrary qubit to Bob with the help of an entangled state initially shared between Alice and Bob. So if I compare this classical versus quantum, to send arbitrary quantum state, classically, any protocol that you design, you require infinite amount of classical communication. On the other hand, if we use quantum mechanics, then it will be, you just can do the task by using 2 bits of classical communication. So you see that here you require infinite, that is very large amount of classical communication. On the other end, here you require only 2 bits. So this is really a infinite resource reductions by using quantum protocol. Now, here just comment, and that's an important one, that here in this quantum teleportation protocol, no faster than light communication. So it's not true that Alice does measurement and immediately Bob's state becomes the one of the state. But this is so. If this would have happened, then there will be faster than light communication. But this is not happening here. So if one can study this carefully, one can find that unless Alice sends these 2 bits of classical communication to Bob, there will be no state transfer occurs. And that means 2 bits of classical communication between from Alice to Bob means that there will be that should follow the relativity, and that should follow the light speed. So there will be no I mean, we are here not really violating the speed of light. So the entire protocol is performed, and we can successfully do that provided these 2 bits of classical communication about Alice's measurement result is communicated to Bob. So as I said, without classical communication, Bob's state remains same, and this can be a nice, actually, kind of assignment to check that if you do not perform any communication, that means if you do not perform any these 2 bits of classical communication, that means if Bob is unaware of the measurement results that happen or that came to Alice's lab, Bob's state remains same. So this one can check easily. So as I am kind of emphasizing, because there is a kind of misconceptions in community that in quantum teleportation there is a information transfer which actually breaks the relativity, and that means you actually breaks the speed of light. It is not true. So just to compare the last day's protocol with the quantum teleportation. So last day we discussed about quantum dense coding, where the task was to send classical information, and today whatever we discuss, it is a transfer of quantum state. The medium that we have used in both the situation is this quantum state. A priori, Alice and Bob has to share this entangled state or the singlet state or an arbitrary entangled state between them. Now here the allowed operations are such that when you talk about dense coding, since we are interested to transfer classical information, that means bits. So no bits were transferred from Alice to Bob. As you remember, if you remember last day's my talk, then we just transfer a quantum state from one place to another. And in this quantum teleportation that today I discussed, their qubit cannot be transferred from Alice and Bob. Instead, there is a measurement outcomes that was transferred. So the classical bit was transferred from Alice to Bob. So here I have used not allowed operations, but allowed operations in this case was quantum state. Here was the bit. So now, as I said, that this is always a question in physics, that this is just a theory, or whether there are some experiments which can successfully tell us about whether this can be performed or not. So I think that quantum technology's advancement actually heavily depend on the experimental observations that are going on for last 30 years. So after this teleportation protocol was proposed in 1993, soon after this was demonstrated in by using several physical systems. And actually, there are several quantum teleportation experiments. Several quantum teleportation experiments have been done in several places around the world. Here, I will just mention briefly about some of the initial demonstration. So the first demonstration by using photons, polarization degrees of freedom in 1997. So by Anton Zeilinger's group, and in Innsbruck, and there they, as it is in the name, that this is experimental quantum teleportation. And as many of you probably understand, that some of the authors are now probably are very famous group leaders around the world. So this was a, kind of breakthrough experiment. So in 1993, the quantum teleportation was discovered, and soon after, like 4 years later, it was demonstrated in Innsbruck. So this was the kind of the protocol, the design of photonic lab, or the photonic table. So as I was saying, that there is always a BBO crystal that you require to create the entangled state. So usually you have a pulse, a laser. You push this laser on the BBO crystal. This is a nonlinear crystal which create an entangled state between Alice and Bob. So you see this one, this two is the, and the three, this is the shared entangled state. So one particle is going to Alice, another is going to Bob. I hope that you are looking at my arrows. So this part is going to Bob, another part is somehow going to Alice. And then there is an input state which are also pumped, and this input state also goes to this part where you use the beam splitter to perform the measurement. And this is the measurement that I was talking in theoretical sense. We have a measurement box, but typically in case of photonic lab, many of you probably know that you have to perform, you have to use beam splitter to do the measurement. So this red line is the initial state, and this one is the part of entangled state, and here the measurement is performed by Alice. Then there will be a classical communication. This classical information transfer can be via phone call, and this classical information transmission happen, and then Bob does some kind of local unitary by the polarization beam splitter, and this they analyze, and finally they can recover the initial state at Bob's lab. Now this can be a table in case of photonic experiment, but now it can be few hundred meters in even kilometers. Now, in case of photons, there are many degrees of freedom. So, for example, 1998 Polzik's group have shown, this is a science paper in 1998, where instead of polarization degrees of freedom, they have done a experiment where they exploit the position and momentum of the photons. So when you have a polarization degrees of freedom, that means you have right circular or the left circular polarization in the previous experiment, that can be mapped as a qubit. On the other hand, when you have a continuous variable system, There the mapping is different, but I'm not going into detail. But just to tell you that with this kind of scenario, also quantum teleportation is done by of optical coherent state by using the entangled state or the squeeze state entangled, the squeeze entangled state, and they also show that they can actually can do the teleportation with certain fidelity which is higher than what you can achieve classical. Now, there are also other degrees of freedom, like path plus polarization degrees of freedom, were used by the Martinez group and this other scientist. And this is experiment was done by in Italy, and there also in 1998 this was reported in PRL, where they have done the experiment. As you see, the 100% success rate of experiment of teleportation experiment done in Italy. Now, in 2004, there are again by David Wineland group, which have done the experiment by using trapped ions. Here, if you remember that last day also, they have done this experiment of quantum dense coding with atomic qubit by exactly these 9B plus barium plus ions. And these are kind of ions which are in a trap. So this is a massive particle that were transferred, and this is also unconditional teleportation. But since this is an experiment, there will be a noise, so the fidelity or the exact state transfer is not possible, but this can be possible with a 78% accuracy. And that was of course in 2004, and later on it was also improved. Now, probably now we are very aware of the superconducting circuit, because this is one of the physical system which are kind of prominent while doing quantum computation. And so this is a Walraff's group which actually have done the quantum teleportation experiment with 86% probable, 86% fidelity. They can reproduce this quantum state at Bob's place by in using superconducting circuit, and this was done in 2012. Now the this is, as I said, that it can be few meters, few kilometers, but now this was in 2000, I think around 10, when there was an experiment which actually was done by again Anton Zeilinger's group between two islands, La Palma and Tenerife, this teleportation experiment. And these two islands are 143 kilometers away, and they have done this 143-kilometer away teleportation experiment successfully. Now, I just want to say that I mean this tells us that, for example, if you have a Hyderabad and Ajanta Ellora, so this kind of experiment is now possible around 200 kilometers, where we can send the quantum state transfer. Now, in trap times, also this 2009, it was by different this ytterbium ions that they have used to teleport this ytterbium ion with 90% fidelity, and that they have down about 1 meter. Now, in trapped ions, these are the massive systems. So here, like polarization degrees of freedom, by using photons, you can go few hundred kilometers. But here, this 1 meter, they can go very small distance. But as I was telling last day, that this kind of protocol is also important, because quantum teleportation not only a communication protocol, but this can be used also while building quantum computer, where between two circuits one has to transfer certain quantum information. Now, here is another experiment where how to teleport quantum information over 100 kilometers over fiber. As we know that optical fibers are nowadays also used to just communicate the classical information. So this same optical fiber can be used to do kind of teleportation. And this was the NIST experiment, which was by using photon. And here they were talking how to really transfer quantum information over 100-kilometer fiber. So the researcher at the National Institute of Standards and Technology have teleported quantum informations carried in photon over 100 kilometers of optical fiber, and this is 4 times further than the previous record. So this is also another breakthrough result where the people are able to transfer quantum informations over 100 kilometers. So today I'm discussing more about the experiment on quantum teleportation, because there are last 20 years, 20, 25 years, there are several breakthrough experiments on quantum teleportation were done. Actually, it's kind of it actually tells us that really quantum communication devices are kind of ready already, and this is really a kind of reasons that quantum technology becomes so popular now and becomes so important in several from several directions. So this is also a matter qubit teleportations, where they, instead of 1 meter, now they can even do teleportations of a massive particle like ions and etc. about 21 meter. So to my knowledge, this is the highest distance that they can teleport massive particle. Now, this is different than the photons that we have already discussed. Photons are massless, that we know. So this is one of the recent experiment which actually tells us that not only we can do a teleportation between two parties, but we can really build a network, which I actually wanted to show. And this is an experiment done in Envy Center in Diamond. Possibly you have heard Envy Center in Diamond in when the Kosturi talked about quantum sensors. And so the Envy Center can also be used not only for quantum sensing purpose, but it can also be used to build quantum network, and that can be useful for many other quantum information processing tasks. So here there are, as you see, there are 3 nodes, and the quantum state has been transferred from A to C. Now this is my last probably half an hour. I will discuss about some directions in which now the quantum network can be built, and this is actually one of the promising field in quantum information science. So, as I said, in next half an hour, I will be talk about how to spread entanglement between several nodes. And there are 2 ways one can do that. One is measurement based, another is gate based quantum circuit. And I will just give a flavor that how to do these protocols in when there are multiple nodes. So these protocols are extremely important and quite challenging experimentally, and the several groups are trying to propose how to make quantum networks, and also people experimentalists are trying to report that how to build quantum networks. This is towards quantum internet, and so this is extremely important. Before I go, I just want to say that if you want to build quantum network, we require multi-partite entangled state instead of two-party. So I just very briefly discuss about what is multi-partite entangled state, what are multi-partite entangled states. So I discuss about three-party system. So suppose there are Alice, Bob, and Charu. They prepare state psi1. So Alice prepares psi1, Bob prepares psi2, and Charu prepares psi3. Then the joint state look like that. These are the fully separable state, not useful for any quantum protocols typically. On the other hand, there can be a situations when two of them, suppose Bob and Charu prepare an entangled state and Alice prepares an entangled state, separable states on her lab. And in that situation, this will be the state, and these are the biseparable states. So there are some kind of two-party entanglement which are in the Bob and Charu's lab. I mean, they share. On the other hand, Alice is completely unentangled with Bob Charu. So these states can be useful. For example, if Bob wants to send, say, quantum state to Charu, but this when Alice, Bob, Charu share this kind of state, then this Alice cannot send any quantum state to Bob or Charu. So these, because this is separable across this bipartition. On the other hand, it is possible to create a genuinely multi-party entangled state which cannot be written mathematically in the biseparable form. So not written like that. And to create these states, their particles should interact. So instead of, so the previous scenario, so a source can prepare a tripartite entangled state and then sends one particle to Alice, another particle to Bob, another particle to Charu. In this way, you can share an entangled state. And Alice, Bob, and Charu cannot prepare these states when they are situated in far apart location. Now, as you see that from this slide, that this is just a three-party scenario. The more complexity comes, and this is the further.
ହଷ୍ଟେଲରେ କ'ଣ ଆଉ ରହିବନି କହିଛି କି?
20 ରୁ ତାର ଷ୍ଟାର୍ଟ ହେଇଯିବ କ୍ଲାସ୍ ସ୍କୁଲ।
Hello, hello.
ଜୁନ୍ 21 ଖୋଲି ଯାଉଛି ନା ସନ୍ଧ୍ୟା?
Hello. Okay. So there are n-party pure states you can define where there can be different kind of entangled states. So as I said that we will be interested to communication network. So this is you can think this dark dots can be the nodes, and finally we want to
ପ୍ରାକ୍ଟିସଟା ଆମେ ଅଧିକା ରଖୁଛୁ ଆଉ ପ୍ରୋଜେକ୍ଟ
connect.
ଗୋଟେ ଦବ
ସେଟା ପଢେଇବ କଣ ସେଇଥିରେ ସେଇଟା ପ୍ରାକ୍ଟିସ ହେଇଯିବ।
ଏତେ ଯାକ କିଏ କରେ କି ସିଲାବସ୍ ଯାକ ସ୍କିଲ୍ସ କୋର୍ସ ଗୁଡା?
Hello.
ଆରେ ଭାଇ ତମ ସ୍କିଲ୍ କୋର୍ସ ବୋଲି ତମ କ୍ୟୁପିଟା।
Others, please mute your mic.
Hello. Yeah, so all these nodes are kind of so these dark spots are the nodes, and you can think that this thin line are the entangled states. And so the ultimate goal is to connect entangled states between all the nodes. So this is what we mean by quantum internet. Just like now we are connected to you, or I am connected to you by several internet lines. Now, this is actually extremely important. So, a network is a collection of nodes connected by edges, as I have said, and sharing entanglement over large distance is a recent challenge, but this is the ultimate goal because we know that entangled states are the resource for all the communication protocols that we know till today. And as it was emphasized in a very nice review article by Kimball, the quantum internet, where the goal is to distribute entanglement across the network and the teleportation of quantum states between nodes to be occurred. Now, this entangled network, actually, the kind of the starting point is I mean, kind of the first kind of this kind of proposal actually came just after the teleportation theory paper in 1993. So this is by Marek Zhukovsky, Anton Zeilinger, Horn, and Eckert, where they proposed a kind of entanglement swapping experiment by using photons. So you see, these are the BBO crystals, which actually you push the laser and create an entangled state. And for a theorist, this is the thing that they are proposing. So suppose S, this is one of the sender, wants to send or wants to share an entangled state with the receiver who is far apart location. Then this long distance entanglement sharing is very hard because it will be more and more noise will be involved. And so they actually choose a middle path. So there will be a middleman, which they call a N1 node. So S will share an entangled state with N1. N1 share an entangled state with R. Then N1, the middle one, the performs and measurements on her or on his lab, so that you can show that S and R can share an entangled state between them. So this is the initial 1993 proposal. This is called entanglement swapping. So even S and R are not shared an entangled state, but with the help of this middle person or middle node N1, S and R can share an entangled state. And this N1 performs again the Bell measurement. Now, this was done by Anton Zeilinger, Marek Zhukovsky, Horn, and Arthur Eckert. This is one of the another breakthrough experimental proposal, and later it was used in all the photonic experiment. And this is also the starting point of building quantum network. So now we prepare a kind of much more ambitious thing. So suppose S and R wants to share an entangled state. You have a m number of, you can think, the nodes in between. If the S and R's distance is high, so you divide it into small segments, the entire path, and S share an entangled state with N1, N1 share another entangled state with N2, N2 share another entangled state with N3, and so on. Finally, N, say K, share an entangled state with R. And all these middle nodes, they perform an entangled measurement, this Bell measurement, and so that finally S and R share an entangled state. Although it looks kind of, say, silly, but this is the only way to share an entangled state between S and R, because this is the way people have seen that noise can be reduced into the system. So you can think that I want to share an entangled state between Kolkata and Delhi, which is 1300 kilometers away. In between, there will be an Allahabad. Okay. So sender shares an entangled state with the Allahabad node, which is N1. Allahabad share another entangled state with Delhi. Then Allahabad performs, this middle node performs the entangled measurement, so that finally Kolkata and Delhi share an entangled state. So this is how we are planning to do an entangled network between a long distance. So if all of them are entangled, all of them are very highly entangled like singlet, this can be easily shown, kind of simple but a tedious recursive relation you can find, by which you can show that S and R can share an entangled state, the same singlet state, if N1, N2, N3, Nk, these middle people help or middle people perform the Bell measurements in their nodes. Now, if all of them are noisy, then this way sharing is not very good, because you can see that for noisy entangled state, there will be a critical noise value between all these entangled states, above which, or I mean, if noise is beyond certain threshold, then S and R cannot share a highly entangled state between them. So this was actually demonstrated by us a long back in 2005, where we show that to guarantee entanglement between S and R, actually less noisy state is required. I mean, less and less noisy state is required if the number of nodes between S and R are increased. So with the increase of number of this middle people, the number of middle man or middle women or middle humans, S and R actually cannot share a highly entangled state. So to get away this, what is a way out? We have also proposed that instead of having a linear chain, you can have a kind of star network, and this where the suppose the S share an entangled state with N1, S share another entangled state with N2, and so on. And the middle one now perform a joint measurement on his or her lab, so that finally the outer circle nodes share an entangled state, multipartite entangled state between them. And this was used also in several recent articles of after our proposal, where this was now more or less established that this is the way one can actually spread entangled state in quantum networks. We have also recently done some, I'm not going into detail, but this kind of star networks you can use in a kind of one dimensional, in a one dimensional lattice, for example, where one wants to share an entangled state between 1, 2, 3, 4, and then one has to perform a measurement in several, say, these blue circles and all these red dots, to share finally an highly entangled state between 1, 2, 3, 4. So what we have found in this work, that what is the critical noise value that we require in each of these segments, so that finally 1, 2, 3, 4 share an entangled state. So this you can go on in a two-dimensional lattice, and for example, triangle, or in a circle, or in a square lattice, and so on. And in all these protocols, you can show that what are the noise parameters that you require, so that finally the entangled state is shared. So this was actually we did in 2020 with some of my students. And moreover, we show that there are in this can also be done, this kind of network can also be done in a photonic device. And we have also used here continuous variable system. So this is the position and momentum degree of freedom of photons that we use to kind of set up a photonic lab, where this was our proposal in this work, where we show how to really share entanglement in photonic device. And soon after, there was a experiment where it was shown that in a metropolitan city, they have done a photonic experiment where they have created a free space quantum networks between four, I think 5 cities were involved. So this is also important, as I was emphasizing. So IBM has recently published kind of roadmap that how to build quantum computer, how to have a scalable quantum computer. And then they said that there will be many small quantum computers which will be linked via some quantum communication link. These are the red lines. And in this way, they can reach scalable 4,000 qubits quantum computer, and these links will be quantum links. So as they said, that this pink one is a quantum link, and this is exactly what I was trying to tell, that how to really put the entangled state between these systems. And this is how. So as I mean to I mean, here I just want to emphasize that quantum communication or quantum network or internet that we were discussing is not only a quantum communication device, but that can be important to have a scalable quantum computer. So here, as I said, that here I discuss about entanglement spreading. So you perform, say, in these red circles, you perform measurement to have this kind of link. But in quantum communication or in computational devices, we may have to delete the link. So again, you can perform measurement and can delete the link. This part I haven't talked about, and I will not be talking. But this is also another directions that we are kind of exploring, where you, without disturbing this kind of subsystem, you actually delete certain links to protect this part. So this can also act as a quantum memory and so on. So I'm not discussing this. So as I said, you perform measurements here, you actually kind of disturb or you delete these two links, and this is how you create deleting the link. Again, the measurement helps, but I'm not going into detail this. And here we also have shown that when this measurement is noisy, how this deleting link get affected in a very recent paper which published I think 1 month back. Now, the last maybe 5-10 minutes, I will be talking about another kind of circuit. So here I can give you a flavor that how quantum network can be built by using measurement. Another way to create quantum network is by using quantum gates. So how to do that? Say, for example, in this quantum computer, suppose I want to build I want to create this pink link in this. So how to do? So these are the small, say, quantum network, or you can think part of quantum computers. This is here. And now I perform a quantum gate between that. So the quantum gates can be a 2-qubit quantum gate. So this is a unitary operator in a 4-dimensional Hilbert space. And this is another 2-qubit, so 4-dimensional unitary operator here. So I apply this unitary operator here and apply this unitary operator here, starting from a 3 independent quantum computer or quantum network as shown in IBM. And in this, by using this quantum gate operation, you actually connect the link. As you see here, I connect this link. Here, all of them now becomes connected. So this, we have proposed that how to create optimally or how to circulate entanglement among these nodes recently by some of my students and Amit, who is a faculty in IIT Palakkad. And we have shown that how to, what are the optimal unitary operator or optimal quantum gates to be used so that we maximize entanglement among the network. So this implementations can be done in quantum circuit. So it can be implemented not only in the in building quantum devices, but that can be used also to build quantum circuits. And in quantum computation, here we find that what are the unitary operators that I have to apply, so that finally the entire network is highly entangled, highly multipartite entangled. And that we characterize and we find out. And not only in this kind of unstructured network, we have also shown that suppose you have a triangular network, and I have these small triangles. As you can see, these are the small triangles which actually is not connected each other. There I perform in each step some kind of unitary operators, the 2-qubit or the 4-dimensional unitary operator, so that finally the entire triangle is in a multipartite entangled state. So how to optimally circulate entanglement in this triangular network, so that finally this triangular, we built a quantum internet which have a triangular shape that we have designed in this paper. So for example, we have shown that each step how many unitary operators to be performed, so that finally the entire system gets entangled, and how it scales with the number of sites or number of nodes in a triangular structure. You can make this exercise also for square and other kind of lattices when there is a structure. So there will be a systematic way how to circulate entanglement between nodes. So, in some sense, I come to the end. So, as I was trying to tell, that people around the world is making a proposal to build quantum internet, and this quantum internet can be important for building quantum computers, scalable quantum computer. At the same time, it can be important also on quantum cryptography, which I will be discussing tomorrow. So this is the, as I said, quantum internet means quantum networks. So that means we want to build a highly entangled states, or we want to somehow connect all the nodes by entangled state. As we know that the entangled states are useful for communication purpose and several quantum information processing tasks. So this quantum internet, as I have said, that it can be a classical information transmission. So as I discussed last day, so quantum internet is built, we have to build quantum internet, means we have to do the entanglement spreading fast, so that all the nodes is connected to entangled to somehow get entangled, as I was discussing. Then these entangled states can be used to do either quantum state transfer or to send classical information that I discussed last day. So this spreading of entanglement can be useful, as I was trying to say, the spreading of entanglement or creating entangled links can be useful for sending quantum state, sending classical information, even to build scalable quantum computer. So thank you very much for your attention.
Thank you so much, ma'am, for your insightful and engaging lecture on quantum communication network. Your insights on quantum gate theory of entanglement, quantum teleportation, and multi-party quantum entanglement in quantum networks has truly added to our understanding. Now, ma'am, with your permission, we would like to have a discussion session. All the participants may address their questions and queries to Professor Aditi Sen.